Hello, welcome to project number 3 in our Intro to C programming course. Like usual, hopefully you'll have done the project already, but if you haven't, that's especially okay this time because our goal involves a kind of advanced C technique. This time you might want to follow along pretty closely. So, our goal this time around is we're going to be outputting the Fibonacci series to the terminal. We're going to be doing this in two different ways. The first is we're going to be using loops. That's just a regular iterative method of doing it. And the second is we're going to be using recursion. In C, and in C-like languages, a recursive function is a function that calls itself somewhere inside of it. These can be a little iffy if you're not careful about how you write them. They can call themselves in an infinite loop, and this can be a real pain to diagnose. Under some circumstances, if this happens, the memory that gets allocated to your process by the operating system will run out and you'll just crash. Sometimes it can loop infinitely. It's a mess when it happens. But for something as simple as this, it really shouldn't matter if we mess up and do that. Fixing it would only be a couple of keystrokes away. If you don't recall, the Fibonacci sequence is a mathematical series. Fibonacci sequence? Series? I don't remember which word is appropriate for this. I'll be using series. The Fibonacci series is a mathematical sequence of numbers generated by starting with the sequence 0, 1, and then every further element in the series is gotten by adding the previous two together. So the third elements in the series would be 1, then 2, then 3, 5, 8, 13, etc. Is my arithmetic right there? Yes, looks like it is. I'm bad at math. That's why we have computers to do it for us. So, what I'm going to do here is I'm not going to have two separate files for this. Instead, what I'm going to do is I'm going to have void Fibo iterative int num int terms. Let's do that. Int terms. And I'm also going to forward declare int Fibo recursive int term. And you'll see why I pluralized one and not the other here in a moment. And the goal of main here is going to be to determine how many terms we want and to determine which method we want to use. The output should be the same, maybe give or take a couple of messages we put out to differentiate them. But I want to have this all in one file, because that makes it easier for me to do all in one video. So, let's break this down into steps here. Steps. Step 1, get number, if I can type, number of terms from the user. 2, get method from the user. Either iterative or recursive. Number 3, run that method, outputting the terms to the screen. So, that is the brief version of what we'll be doing. By now, hopefully you've watched the other two videos or done the previous projects yourself. We should know how we're going to get input from the user. We're going to prompt them using printf. So printf input the number of Fibonacci terms you want to see. And we're going to use scanf again because... No, you know what? I said I put in the comments of my last source code file that I would show the memory safe way to to get user input. So a hiccup we ran into last time. Let's see if I can replicate it here. We're gonna say int terms scanf %d address of terms. And if I'm correct, let me hit save here. Ignored return value. Maybe that's not quite right. Let's try hitting that. There's what we wanted. It says down here, scanf, this function or variable may be unsafe. Consider using scanf_s instead, yada yada yada. What I did last time to disable this was I just did a pound define that told the compiler to ignore those warnings. This time around, I'm actually going to do the memory safe thing. So the reason scanf is not memory safe is because when you pass it a pointer, you could be passing it a pointer to anything. And it can't possibly tell the difference between, say, an int pointer or a character pointer or a pointer to a string or a pointer to some other structure or even a pointer to a function. And so it's entirely possible that we could do something like this. Char temp, and then we would say scanf, put a whole 4-byte integer into this 1-byte space here. You can't do it. What'll happen is it will try to load, it'll load the first byte into temp, and then the next 3 bytes are going to be next to temp in memory we don't have access to. If this happens in the wrong place in memory, our whole program will crash because we've gone into memory we're not supposed to. Bad idea. So here's what we're going to do instead. We are going to define an array of characters. We'll call it buffer. And I'm going to say have it as a 64-byte buffer. Remember, characters are 1 byte, so this whole buffer is just one 64-byte long chunk of memory. We are going to, instead of using scanf, we're going to use a function called fgetS. What fgetS does is it just gets an entire line of text up to max count. You can see it might be a little small on the screen. The second argument for fgetS is the maximum size of the buffer that you're passing it. And it'll get it from any file stream that you tell it to. So that can be from standard in, that can be from a file on the disk, that can be from some other device hooked up to your computer. So let's do this. We're going to pass it buffer. Max count is 64. And we're going to get our input from standard in. Is that going to complain to me about that? I don't know. Let me save this. Try building it, see what happens. Cool, doesn't complain. Good to know. I'm not using keyboard shortcuts in this, in part because an extension I use, I had to disable it for this, and now my keyboard shortcuts are all kind of messed up. This is actually good for the purposes of the video, because it means I have to go through every step one at a time. Let's not put that there. So if I want to save it, I have to go all the way up to File, hit the Save button. If I want to run it, I have to go all the way up, hit the Play button. Alright, so let's keep going here. Now we have a buffer full of characters. Int terms equals 0. How are we going to turn that character buffer into the number that we want? We're going to use a function called a to I. A to I stands for ASCII to integer. It just converts a string of ASCII characters into an integer to the best of its ability. If it sees anything that isn't a number in there, it's going to get confused and stop. If it sees a period in there, it thinks it's a floating point number and it might get confused, it'll just stop. Old C functions can be kind of finicky in that way, but they're very reliable when you use them the way they were intended. So, in order to do this, we're going to say terms equals a to I buffer. Identifier a to I is undefined. Give me just a moment here to Google something. Okay, we're back. I figured out why it didn't know what A2I was. It's because I forgot to include. A2I is not in standard IO.h. It is in standard lib.h. So, now we got that. A2I is defined. We're good to go. Let's keep going here. Next things we need are we need to prompt for which method we're using. So printf, do you want to use the iterative method 0 or the recursive method 1? And so what we're going to do here is if the user inputs a 0, we're going to use the iterative method. If the user inputs a 1, or actually we're just going to say anything that isn't 0, we are going to we're going to use the recursive method. We could make sure that it was either a 0 or the 1, but that would honestly kind of waste our time and not be the point of the exercise here. So we still have buffer. Buffer is still perfectly usable, so we're going to fgetS buffer 64 standard in. Same thing as last time. It is going to get up to 64 characters from standard in. Actually, more accurately, it's going to get up to 63 characters from standard in. fgetS makes sure that the last character in the buffer it has room to be the null character at the end of a string. And just a quick refresher, strings in C are just strings of bytes, like any kind of byte, with a null character, or a byte that's all zeros at the end. As long as the whatever is reading a string doesn't find a byte that's all zeros, the string is considered to be unfinished. All right, let's get going here. Now we have buffer. Let's say int method equals 0. Method equals a to I buffer. And now we're going to do our last bit here. If method equals 0, then we're going to use the iterative method. So we're going to call, what was I called it up here? Fibo iterative terms. And if method equals 1, we're going to use the recursive method. I'll write the recursive method last. So, first thing we want to do, let's just go ahead and get the function for the iterative method out of the way. We already have declared it up here, so we can actually put it lower than main in the file. So, void fibo iterative int terms. What do we need for this? Well, we know that the first two terms are defined for us, so let's say int first equals 0, int second equals 1. Int current. I want a variable to keep track of what of what term we're on in the series. I think I'm just going to call that cur, short for current, equals 0. 0, 1. I'm going to say 0 will work for now, and if it turns out to be wrong, I'll switch it to 1. Typically, when you're counting in a program, you're going to start from 0 instead of starting from 1, because usually you determine when you've gotten to your goal using the less than operator, which means that 0 will be the first, and whatever your goal is minus 1 will be the last one. So, let's determine what I'm doing here. That's the wrong button. I've got something up on my second monitor right now to just check my own work here. Let's see here. We want to loop through up until the number terms. So let's just use a for loop for that. For cur equals 0, cur less than terms, plus cur. Let's see here. We know the first two terms, so we can actually kind of skip them. But we don't want to actually skip them because, well, we need to print out this series to the screen, and we're going to do that in this function instead of returning values one at a time, because that doesn't quite work for this. So how are we going to do that? Let's say if cur equals 0, printf %d new line character first, else if yeah, let's just do it like this. The minor overhead here isn't worth considering. So there is a slight performance downside to the way I'm doing this, and that's that cur will be checked against what's going to happen is these conditions will fire every time. I think I have a way around that though. If cur equals 1, printf %d /n second. And I think my way around that is doing this. If cur greater than or equal to 2. So here's what this is going to do. First time around, the first time this loop runs, it's going to run into this condition. It's going to say, well, no, cur is 0, so it's not greater than or equal to 2. It's going to go down here. Yes, cur is 0, and so it's going to printf this. Then it's going to skip this because it's behind an else, and go back to the top. ++ cur will fire. Cur will be 1 now. Cur is not greater than or equal to 2. So we're going to go here. Cur is not 0. We're going to go here. Cur is 1. We're going to print this. This ensures that these two conditions are checked as little as physically possible. That's kind of a micro optimization, but it makes me feel good to do it that way, so I am. The reality is checking these conditions takes less time than it takes to blink, so really it's an optimization for aesthetic purposes more than anything else. So let's actually get to this. We're gonna say int next term first plus second. Then we want to move, then we want to kind of shift those terms back because we're going to be using these later. So what we're going to do is first equals second, second equals next term. So let me see if I can explain what this is actually going to do here. When we start out, first is 0, second is 1. Another way to think of what these two variables represent is two elements previous and then one element previous. And so what this is doing is we're saying whatever was one element, or whatever was two elements back, we're going to set to what is currently one element back, and whatever is one element back, we're going to set to the current term. That way, the next time around, we will have the correct values in place. If we want to be extra sure that what we're doing is correct, when we output this, we can actually give ourselves a little bit of extra information. So printf %d. Here's what I'll do. Yes. Okay, here's what I'll do. Printf %d term number %d colon space %d. And then the first number we're going to pass to printf is going to be cur plus 1. And then the second number we're going to pass is next term. Then at the very end of this for loop, we're going to printf one more thing. Put a space here because we didn't do that before. And this will help us format everything. Previous terms %d %d. First, second. So what this is going to do now is the first time this function runs, this check will fail, this check will succeed, so we'll printf 0. Then, before we go back to loop again, we will print previous terms first and second. In this case, it'll be 0 and 1. Second time this runs, it'll do the same thing, except this check will fail, this check will fail, this check will succeed, so we'll print 1, previous terms, 0, 1. Third time this loop runs through, this check will pass, so we will get 1 as a result of first plus second. First will become 1, second will become 1, and we're going to printf 1 as our term, and then we're going to get 1 and 1 for this. This might be a little confusing. Let me see if I can think this through real quick. If I... No, you know what? No, I think this is the best way to do this. So I'm actually just going to reword this. Currently held terms. This is more accurate. This will tell us which two terms of the sequence are actually being held in memory right now. And this will tell us whether we're doing things right. So just to make sure that I know what I'm doing, save this. I'm going to give this a quick test run. Assuming it compiles. It does compile. Let's zoom in here for real quick. I want the first 5 terms using the iterative method. I forgot to add a new line character. Try that again. Uh, 5, 0. Cool. That looks like what we wanted. Cool. Yes, I believe I'm doing this right. Just to check one more time, I'm going to do the first 10 terms. 10, 0. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. That looks correct to me. And all of the values that are being held in memory look to be the ones we expected them to be. So, cool. I am going to say this is working. Let me remove these new line characters. Actually, no, I want these. Because now that I know that this is working correctly, I don't need this printf statement anymore. I do want this term number %d, and I want term number %d, cur plus 1, cur plus 1. Test this one more time. 10, 0. What have I done wrong? I didn't have the new line character again. So you can see what happens when I don't put that new line character in, is the line just never stops. And so I have all of my things on one line here, and it's the ugliest thing in the world to read. Let me fix that. But I know that this fix will work because I saw what I did wrong. So, the iterative one now works to our expectations. To run through this real quick before I move on to the recursive one, we know the first two values of the sequence. They are part of the definition of the sequence. And this value cur here represents which term we are on in terms of how many we're trying to output to the screen. So we have a for loop here for cur equals 0 less than terms. If we are beyond the predefined, if cur is greater than or equal to 2, if we have already output the first two terms to the screen, then we calculate the current term by taking the previous two that are held in memory using first and second. Then we shuffle around the values of first and second by essentially bumping each one back, or bumping each one forward a term in the sequence. And we output the value we calculated to the screen. If we are just outputting one of the two predefined ones, we do it like so. With that out of the way, it's time to actually do the recursive method. So how are we going to do this? We're going to start our new function here. Int Fibonacci. That's what I named it. That is, in fact, what I named it. Int term. So, like last time, the first two terms are predefined. The difference is, this time, instead of holding them as values in memory, we're going to... This function is going to calculate the term that is asked for on the fly every single time. This is going to be pretty slow, actually, compared to the above version, but it is a pretty easy way to demonstrate how recursion works. If you ever take an algorithm analysis course, you'll go into detail as to why this method of calculating the Fibonacci sequence is actually really slow. If term equals 0, or term... Ooh. That's a question. Let's consider that 0 the first term and not the 0th term. I'm doing this specifically... I have to come up with a standard for myself here, where if I mix up my definitions, if I say... If I say it's okay to ask for the 0th term in the Fibonacci sequence, counting it might get a little weird. So really this is kind of an arbitrary decision on my part. So let's say if term equals 1 or term equals 2, return term minus 1. So what this will do is if we ask for the first term, this will, this whole check will evaluate to true. If we're asking for the first term, this part of the check will fire, and we will return 0. So that's 1 minus 1 is 0. If we ask for the second term, we'll do the same thing, except we'll return 1. That's 2 minus 1. And specifically, this is what's called an exit condition. You'll notice this part of the recursive function doesn't call itself. It returns a definite value. So whenever we ask for the first or second term of the Fibonacci sequence, we don't have to keep calling ourselves to further calculate it. However, else return Fibo recursive term minus 1 plus Fibo recursive term minus 2. This is the fun part. So let's say for a moment that we ask for the 5th term in the Fibonacci sequence. So what we pass as term is 5. What's going to happen here is this check will fail the first time. So we'll go down here and we'll say, okay, return the 4th term of the Fibonacci sequence plus the 3rd term. Well, now we have to call our own function twice. So this time we're going to, for this part, we're getting the 4th term. So we're passing 4 here. These fail. In order to get the 4th term, I need to know the 3rd term and the 2nd term. Well, that's a bit rough, because now I have to do the same thing again. I need the 3rd term plus the 2nd term. And what this actually forms is a tree structure. So in order, let me see if I can draw it down here. In order to get the 5th term, let's see, let's do that here and here. I need the 4th term and the 3rd term. Can I put things in the right place? I guess not. That'll work. In order to get the 4th term, let's see here. Let's do that there and that there. I need the 3rd term and the 2nd term. The 2nd term is one of the terms I can just get, but for the 3rd term, I need... I'm so bad at drawing with ASCII. But for the 3rd term, I need the 2nd term and the 1st term. And you can kind of see how this keeps getting bigger as you ask for greater terms. And the issue with this is absolutely none of these terms are stored in memory. Every time I ask for the 3rd term, which you can see I'd be doing a lot, every time I ask for that 3rd term, it has to be recalculated all over again. That's kind of the inefficiency of doing it this way. But we have done it, and it's actually fairly elegant. So this function, unlike the iterative function, this function doesn't actually output anything to the screen. It just returns the number we ask for after thinking about it for a while. What we're going to do for output is do this. For int I equals 0, I less than terms plus I. Printf percent, let's see, term number %d, new line character. So same format string is down here. This time we're going to be doing I plus 1, Fibo recursive I plus 1. Because remember, down here we said that there is no 0th term. In fact, just to hammer that home, if term equals 0, I'm going to give it something ridiculous. Return minus 9999. Do not ask for the 0th term. So in this implementation, we define the first term of the series as 1, and the second term of the series as term number 2, as opposed to defining them as term number 0 and term number 1. Which means, since we're starting from 0 here, we have to add 1 to I whenever we use it. If I really wanted to, what I could do is instead this. So say start I from 1 and then use I less or equal to terms. Actually, I think that is what I'm going to do. I like reading that better now that I look at it. And it matches up with what we defined earlier. So now let's test that and see if it actually does what we expect. So let's get the first 20 term. Not 20. 20's a lot. Zoom in here so you can see. I'm going to get the first 12 terms. And I'm going to use the recursive method, so I'm going to type in 1. Let's see. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. All of that looks correct to me. So I think this passes our test. Cool. So, hopefully this has been informative to you. I know I kind of trailed off a few times and went in weird directions trying to figure out how I wanted to format the output, but this is a pretty accurate representation of my thought process over the course of writing this. Yeah, thank you for watching. Feel free to tinker with this code yourself, and I hope you had fun.